Hello. In today's experiment, we will measure the thermal conductivity of 5 different materials. I have a sheet of glass here, that is one material. I have a sheetrock. Well, sheetrock is drywall, is that right? I have a piece of plastic called Lexan. I have a piece of wood, right? And I have a piece of masonite. So these are the 5 materials. We will measure the thermal conductivity. Now, what does thermal conductivity means? If you maintain the 2 ends of this material at different temperatures, if on the left end it is theta 1, on the right end it is theta 2. There's a temperature difference, theta 2 minus theta 1, depending on which is greater. Now that means heat will flow from the hot end to the cold end. Now the question is, what are the factors on which the thermal current, what's thermal current? The rate at which the heat flows. What are the factors on which the thermal current depend on? Well, thermal current can be written as delta Q divided by delta T. This is the rate of flow of heat. And you know that the rate of flow of heat, which is the thermal current, is proportional to the area across which the heat flows. Is that right? Yes, greater the area, greater will be the thermal current. Another factor on which it depends on is called the temperature gradient. In other words, the fall in temperature per unit length. If delta theta is the difference in temperature and delta x is the thickness of the material, the delta x. So if delta theta is the difference in temperature and delta x is the thickness, then the temperature gradient will be delta theta divided by delta x. So the rate of heat flow is proportional to the area and the temperature gradient. That means I can now replace the proportionality by an equal sign adding a constant. And there we have delta Q over delta T equal to a constant K times A delta theta over delta X. And this K is what we call the thermal conductivity of the material. Alright. Let's talk about the unit. What is the unit of the thermal current? Delta Q over delta T. Delta Q, the amount of heat, is measured in joules. So this is joules per second. Therefore, the unit of this will be a watt. And the unit of area will be meter squared. Unit of delta X will be meter. Unit of delta theta will be Kelvin. So can you tell me what will be the unit of K? This meter and 1 meter will cancel. So the unit of K will be watt per meter per Kelvin. And solving this gives you an equation for K. What is K equal to? K can be written as, this K will be equal to delta Q times delta X. Is that right? Delta Q times delta X divided by A delta T delta theta. A delta theta delta T. Now, that is the equation for the thermal conductivity. Is that right? It's delta Q multiplied by delta X. The difference in temperature multiplied by the thickness of the material our area A. Now, the area is not the area of the surface. We are going to use a block of ice on one side. Now, the heat will be conducted across that area. So, we need to measure the area of that ice block. Okay? I will help you do that. And so, this K will be measured in watt per meter per Kelvin. So what are the things that we need to measure? We need to measure delta Q, the thickness of each material. Well, delta X, the thickness of each material. We need to measure the area of the ice block. I will tell you how to measure it. We need to measure delta theta. Now, in our experiment, one side will be ice and the other side will be steam. That means our delta theta will be 100 Kelvin. So you can use delta theta to be 100 Kelvin. And delta T, we are going to measure this delta Q. You see, we're going to have ice on one side and steam on the other side. Means the heat will be conducted through this material. Heat conducted through the material will melt ice. And we will collect the melted ice for a certain amount of time. That time will be 10 minutes. So our delta T will be 10 minutes. We will collect the melted ice for 10 minutes and measure its mass. Now, if certain mass, certain amount of water, certain amount of ice, if m kilogram of ice melts due to the amount of heat delta Q, then that delta Q will be equal to the mass of ice melted multiplied by the latent heat of fusion. I have given you the value of that in the lab manual. So delta Q will be the mass of ice melted. That is the experimental part. We will measure the mass of ice melted. In other words, the mass of water that is the result of melting ice. If m is the mass of ice melted during a time delta T, that delta T will be 10 minutes, 600 seconds. Then delta Q will be that m times LF, the latent heat of fusion. The value will be 3.34 times 10 to the 5. I've given it to you there. So once you have all those values, we can calculate K. So we can now start our measurement. First of all, in order to measure the thickness of these materials and the area of the ice block, we need to use the vernier caliper and the screw gauge. So if you are not familiar with the use of this, let me take a couple of minutes first to tell you how to use it. This is a vernier caliper which has a vernier scale. Now this is the vernier scale, this is the vernier 0. Now the vernier can be moved along the main scale like this. That means there is a gap created here. You see, this gap, the length of this gap is equal to the distance moved by the vernier 0 from the main scale 0. Now, when you want to measure the diameter of, let's say I want to measure the diameter of this, so what I will do is I will insert in there and I will work the vernier back so that it is properly gripped in there, and I'm going to measure this gap. And look at the way I'm going to measure it. I can use the main scale to measure up to what division? I can measure on the main scale up to 4.2 You see that? 4.2 centimeter. And what is now remaining after 4.2 centimeter? What you need to look for is which of these vernier divisions is exactly in line with the main scale. Now, if you look at this one, now look at this one. This is the 5th vernier division, 6, 7. Isn't the 7th division exactly in line with a main scale? Yes. Therefore, the reading, the length of this gap is 4.27 centimeter. And the 7 came from here. The 7th vernier reading is exactly in line with a main scale reading. So we got 4.27 centimeter as the reading. Okay? Use it like this when you want to measure the diameter of the ice block. This is a micrometer screw gauge, the same kind of micrometer we used in our last lab. Now, there is a linear scale and a round scale. When you rotate the round scale, it moves along the linear scale. Now, the distance moved by the round scale along the linear scale is the same as the gap that is created there. So, if I now want to measure the thickness of one of our materials, I will work the screw back to create the space, and I will insert the material in that gap. There you are. And work the screw back until I hear that tick sound, means it is sort of firmly gripping there. Now, I want to measure the distance moved by the round scale along the linear scale. Now, to do that, you've got to start here. If you notice the linear scale, this is 0, this is 0.5, 1, 1.5, 2, 2.5. That's how the reading goes. So all these are 0.5s. If this is 2, this is 2.5, 3, 3.5, 4, 4.5, 5. Now, I can read, if you look here, I can read up to 5 point, well, I can read up to 6. Is that right? Can I read up to 6 there? What is the best I can read here? That's our 5. Next is 5 point, well, next is 6 millimeter, and I can read up to 6.5. Now, what is left is, look at the readings on the round scale. Which of the round scale reading is exactly in line with the linear scale? That seems to be 46, is that right? It's between 45 and 46. You can take either 45 or 46. Now that means the linear scale reading is 6.5. Well, I don't think there is a 0.5 there. This is up to 6. I can read up to 6 millimeter, and the round scale reading is 45, and multiply that with 0.01, the least count, and so this reading is now 6.45 millimeter. You see that? 6.45 millimeter. Well, let me show you another one now to read. Now, what is this reading now? I'm going to... Okay. Tell me, what is this reading now? If you watch here carefully, You can read up to that 5, 6, 7.5. I can read up to 7.5 here. And the round scale is 43. Now 43 times 0.01 is 0.4. 7.5 plus 0.4 is 7.9 millimeter is that reading. So learn to read this carefully. We will be using this to read the thickness of each of these material. Okay, then why don't we do this? Let's measure the thickness of each of these sheets first to begin with. Alright, we can start with masonite. Alright, let me take the masonite out and let's measure the thickness of that. Work the screw back. Okay, there I have the gap created, and I want you to read this now. First of all, read the linear scale and see how much you can read on the linear scale. If you want a little help with this, you can see the linear scale reading is actually 12.5 millimeter. 12.5 millimeter. And the round scale reading is 15. 15 times 0.01 is 0.15. So the actual reading is 12.5 plus 0.15. That is 12.65 millimeter. Is that reading 12.65 millimeter. Okay, the next ones you need to read on your own. Alright, what's the next material? I'm going to use wood now. Alright, next we will use wood. There, this is wood. Alright, take that reading. Wait a second. Alright, take that reading. Done it? Okay, we finished with wood. And now the next material is Lexan, and here it is. I'm going to bring it and put it in the gap there. Alright, take that reading. Okay, we finished with Lexan. Now comes the sheetrock. Alright, here is the sheetrock. Alright, take that reading for the sheetrock. Okay. And finally, glass. I'm going to bring in the glass and take that reading for glass. Okay, we have now the delta X values for all the 5 materials. Let's now read the method of the experiment. procedure, measure and record the thickness of the material delta X, which we already finished. Now let's start with the masonite and look at the equipment we are going to use. This is the steam chamber. I will let steam to go into this and out. So inside there will be steam, and we will keep the material in here. Well, I can open it up, create enough space for this material to be kept in place. There you are. So the material is going to be on top of the steam chamber. It will look like this. Okay, and now this is the block of ice that if you read the second step, run the jar under water. I have run water under the jar so that the ice is now loose. I have a loose block of ice. Well, it has gone hard again. There you are. This is the block of ice that we're going to use. This block of ice is going to sit on top of this before we start the steam. Alright. Next it says, measure the diameter of the block of ice. Now, I have the block of ice here. I need to measure the diameter, so I'm going to work. Alright, there I have. Okay, now I want you to measure this. I'm going to focus the camera onto that now. Can you read it? Let me move it slightly. All right, take that reading. That is the diameter D1 of the block of ice. Okay, alright, what is the next step? It says place the ice jar on top of the sample so that the open end is in contact with the sample, and let the ice sit for several minutes so that the sample melts and comes in contact. Do not take any data at this time. Let's go to step 4. Obtain the data for determining the ambient melting rate of ice. We need to measure the amount of ice melted during the time delta T due to the heat in the room. Now, we are not passing the steam now. So, what are the steps that we need to do? Determine the mass of the small beaker. I have a small beaker here. We need to determine the mass of that. You are familiar with the scale. Remember, this is read to 2 decimal places, 0.00, and measure the mass of the beaker and record it as lowercase. Now, just record it as the mass of the beaker. Now, the second step, collect the melting ice in the beaker for 10 minutes. So I'm now going to keep this beaker and collect the water for 10 minutes. I'm going to turn on a stopwatch and measure the time for 10 minutes. Measure the mass of water that is melted due to the heat in the room, the ambient heat. Alright? And you can see the beaker there collecting the water. This is the ice. and the steam is now passing. I will collect the water for 10 minutes. I have now collected a mass of water, which is the mass of ice melted during 10 minutes, and I want you to measure the mass of that. Okay, let me focus it on the camera. There you got, this is the mass of that water plus the beaker. So find the mass of water alone, and that is your lowercase m. Record this as lowercase m. Okay? And now I'm going to allow the steam to pass through so that I can collect the water that is melted due to the heat conducted. So I'm going to pass the steam into the steam chamber. And I'm going to wait for some time. I need to wait for some time so that the heat goes in through the chamber and out. And then I will collect the mass of water for 10 minutes. I have now collected water for 10 minutes due to the heat conducted from the steam and the ambient. This is the combined mass, and let's measure that. Alright, let me focus the camera onto that now. Alright, measure this mass. Of course, subtract the mass of the beaker, and that will be your uppercase M. The uppercase M. And uppercase M minus lowercase m will be the mass of water melted by the heat conducted alone. Okay? Now we will measure the diameter of the ice one more time. There I have. Okay, and I want you to take that reading now. This is the D2, the new diameter, and let me see if I can focus that for you. Alright, take that reading. This is D2. And the material that we have been working with is masonite. So for masonite, the diameter of the ice is D1 plus D2 divided by 2. D1 we measured first. This is D2. Take this measurement and record it. Alright? Let's now repeat the experiment for the second material, that is wood. Alright, we need to start by measuring the diameter of the block of ice. So let's do that first. Measure the diameter of the block of ice. There I have the ice. And measure this diameter. Alright, take that reading. Let me focus that for you. This is D1 for the second material, that is wood. Take that reading. I have now collected the water melted due to the ambient heat. Alright, measure the mass of measure the mass of water, that is the mass of ice melted due to ambient heat. Now, we need to find it. Is that right? Yes. Alright, this is the mass of the beaker plus the water melted due to ambient heat, and record this. Find the mass of water alone, lowercase m. We will now pass steam for 10 minutes and measure the mass of ice melted due to the ambient heat as well as the heat conducted through the material. Alright, I'm going to start the time now. We will now measure the mass of water that is collected by melting the ice due to steam as well as the ambient heat. Alright, let's measure the mass. There we are. Can you read it? Measure this mass and subtract the mass of the beaker. That will be the uppercase M, the mass of ice melted due to conducted heat alone. We will now measure D2, the diameter of the ice. Alright, let's measure the diameter of the ice now. There it is. It's not very different from the initial value. Alright, let me focus the camera onto the vernier. Alright, take this reading. This is the diameter D2 for the second material, that was wood, isn't it? Yes. Diameter D2 of the ice. We will now start the third material, that is Lexan. And I'm going to start a new ice block. We will start by measuring the diameter of that ice block. Okay, let's do that. There it is. Alright, measure that diameter. Let me focus the camera for you. Okay, you got a measure of that? Right. And I have measured I have collected the amount of water due to melting of ice due to ambient heat, and I want you to measure the mass of that now. Let's measure the mass of ice melted due to ambient heat. Okay. Let's find where that is first of all. There it is. Well, this is the mass of the water the mass of ice that is melted due to ambient heat. That's the measure. This is the mass of the water plus the beaker. Subtract the beaker, that will give you the lowercase m. Okay, and we're going to we have now measured the ambient heat 3 times. We are now going to take the average of those 3 measures and use it for all the 5 materials, our lowercase m. I will talk to you about that at the end of the experiment. I will now connect the steam and I'm going to let the steam in and wait for some time so that the temperature reaches about 100 degrees in the chamber. Alright. Okay. Steam has been passing for a sufficiently long time, and I'm now going to collect the water for 10 minutes. Now this will be the mass of water melted due to ambient heat plus the steam, the heat that is conducted through the material. And the material we are using now is Lexan. Well, we have been collecting water steadily. I will not keep recording all that 10 minutes, but I want you to see how the experiment proceeds, because I want you to comment on this as you write your report. Again, this is the steam chamber that you see underneath here. That's the steam chamber here. The steam goes in here and out, and you can see that's the experimental material, and that's the ice. So one side of the material is ice and the other side is steam. Okay? Well, I have now collected water for 10 minutes. The mass of water melted due to ambient heat as well as heat conducted through the material. So measure the mass of this water and calculate the uppercase M for the material Lexan. Alright, there you have the mass of the water. Alright, take that measure. Done? Okay. We now need to measure the diameter D2 of the ice, and let's do that. The diameter D2 of the ice, and give me a second, I need to readjust it. Alright, now take this measurement, and that is the diameter D2 of the ice. Okay, I think I need to move the camera a bit. Well, there you are, and take this diameter. This is D2, diameter D2 for the material Lexan. And as I told you, I am not going to measure the ambient heat for the next material. That means this diameter can be used as D1 for the next material. Alright? Well, we will measure that anyway because it's going to take me a couple of minutes before I set it up. So we will measure that diameter again. We will now use the fourth material that I suppose is sheetrock. And although I said we will not collect the water melted due to ambient heat, I have done that. And let's find the mass of that now. Okay, give me a second. Alright, can you measure the mass here? That's the mass of the water melted due to ambient heat for the fourth material, sheetrock. I hope you can read those figures. That's actually 64.14. Okay, that is your beaker plus the water. Obtain the lowercase m from there. And now you need to measure the diameter D1 of the ice. Let's do that. Now there's the ice. Let's measure the diameter D1. Alright, give me a second. Okay, that's the diameter, and measure that. Alright, there you are. Diameter D1 for the fourth material, that is sheetrock. Okay. We are now ready to collect the water melted due to heat that is conducted through the material as well as the ambient heat. And we will collect it for 10 minutes. Okay. Alright, we are now ready to measure the mass of the water that is melted due to heat that is conducted through the material as well as the ambient heat, and I hope you can measure this mass. There you are. Calculate the uppercase M from here. And now we got to measure the diameter D2. Let's do that one now. Okay, let's take the ice out and measure the diameter D2. There you are. Okay. There we go. Let me focus that for you. Alright, take that measurement, diameter D2 for the second material. We have now one more material to go, and I will now measure the ambient heat for that. We'll now start with our last material, that is glass, and let's collect the water melted due to ambient heat for 10 minutes. Okay. I have now collected the water that has melted due to ambient heat for 10 minutes, and I want you to measure the mass of that so that you can get the lowercase m. Alright, let me focus the camera onto it. Now these masses are not very different from one another. They all seem to be the same value. Is that right? Well, approximately. Alright, measure that value and obtain the lowercase m for the last material, that is glass. Okay, now we want to measure the diameter d1 of the ice. I have actually used a new ice, and so let's measure the diameter. Okay, now let me get the ice out. There is the ice. Let's measure its diameter. Alright, let's see if this is right. Okay, there you have the diameter of the ice. And let's try and focus it onto there. Alright, here is the diameter. I hope you have been reading these, taking these readings correctly. It is, this is the way the reading comes: 4 centimeter, 5 centimeter, 6, 7, 8, 9, and you will be always taking the reading corresponding to this. This is the vernier 0. Alright? Okay. Alright, so that is the diameter d1 of the ice, and I will now wait for the water to boil so that I can pass the steam. Ready to collect the water that is melted due to the heat conducted through glass. Alright, let's start collecting that now. Okay. Mass of water that is collected for 10 minutes due to the heat conducted through glass alone. But in this experiment, I want you to take one simple difference. Now, there is actually more water than could be filled in this small beaker. Therefore, I had to collect a second dose. So, I'm going to measure the mass of this in this big beaker. As a result, you need to find the mass of the beaker first. So, this is the mass of the big beaker. Okay. And I'm going to put all that water into the big beaker so that you can obtain the value of uppercase M, the mass of water alone. Okay, there we got. I'm going to put the water in there, measure the mass of water, and there you are. That's the mass of water and the beaker. And now remove the mass of beaker to get your uppercase M for glass. Alright. Okay. Now let's measure the diameter of the ice. Alright, there it is. And I will focus the camera for you. Let's measure that. Alright, that's the diameter, the D2 for glass. Okay. Now you have for each sample a diameter D1, a diameter D1 and a diameter D2, that is before and after. Take the average of that, that will be the average diameter, and half of that will be the radius, and calculate the area as A equal to pi r squared. So for each sample you have the area of the ice that was in contact with it. Then you have for each sample you have the lowercase m. You got lowercase m. What is lowercase m? Well, let me take away this. And what is lowercase m? Mass of ice melted due to the ambient heat, the surrounding heat. And then you have uppercase M, mass of ice melted due to heat conducted through the material and also due to the surrounding heat. And therefore mass of ice melted due to the heat conducted through the material alone is m minus m. And the quantity of heat delta Q will be m minus m multiplied by latent heat of fusion, which is 3.34 times 10 to the power of 5. And this is delta Q. So you got delta Q. I'm sorry, that's not delta theta, that is delta Q. You got delta Q and you have A. Delta theta is the temperature difference between the ice side and the steam side. And I think initially I told you that is 100. Actually the temperature doesn't reach 100. I want you to use delta theta equal to 96 degrees Celsius or 96 Kelvin. Delta theta is 96 Kelvin, and delta T is the time during which the heat has been passing, that is 10 minutes. So delta T is 10 minutes, which is 600 seconds, and you have measured delta X, the thickness of each material. So you have all the information needed to measure the value of K for each material. Okay, well, this has been a very tedious experiment, well, for your partner, not for you. I have been with this experiment now over 3 hours. So you can imagine the extent to which you need to organize and work on this. It takes a very long time. All heat experiments are tedious, but you get all the data neatly. So I want you to give me a critical analysis, your impression of the experimental arrangement, and I'm sure these kind of experiments will give you large errors, and give me some of the reasons why you get that large errors. Alright, so I want to hear from you so that I know you have been part of the experiment. Okay, now I think this is all the heat experiments we will be doing, and in the next lab I will be doing an optics experiment. In the theory we will not be dealing with optics, so we will have some opportunity to talk about optics. Okay, I will see you for that lab later on.